Hey guys, welcome to our lesson on Math 112, section 7.3, solving trigonometric equations. So there's a few different kind of ways to think of solving a trigonometric equation. Traditionally, anytime we solved an equation, what we were looking at is we were looking at what singular or maybe a couple, if it was like a quadratic, a couple values or polynomials, we might have multiple values satisfy the equation, make the equation true. With trigonometric equations, there are an infinite number of possible solutions depending on what type of function we're looking at, because we know that trigonometric functions are cyclical, right? They just kind of go in a circle, right? If we think the unit circle, those angles just wrap around. So any coterminal angle will have the same sign values, which means our solutions to any of these equations, if we want all of them, not just on a fixed interval, they will be any coterminal angle to kind of the basic ones. So what we want to do here is we want to first, on this first example, we're just going to solve these within one positive rotation. So in other words, we're looking at 0 to 2 pi radians or 0 to 360 degrees. Now, since 0 and 2 pi or 0 and 360 are the same angle, we're not including that endpoint. If you look at example 1, you can see those interval notations. 0 is included, but the end, kind of a full rotation, is not, because it's coterminal to 0. So let's solve this first one here. So it wants us to solve the equation on both 0 to 2 pi, so that means we're solving it in radians, and 0 to 360 degrees, so we're looking at the degree version. So we need to get both sets of solutions. Now, this is really easy when we have our unit circle. So what we're looking for here is we're looking for when the sine of x is equal to the square root of 3 over 2. If you remember from the unit circle, sine is the y value. Back up a little bit. So we're looking for within one rotation, which y values are root 3 over 2. And since that's the y, we know it has to be a positive root 3 over 2, so it means it has to be an angle in this first half rotation. We just kind of look through, we see, right here, we have root 3 over 2. So that's that value, which also means it's that degrees. And then we keep going around and we see right here as well. So we've got these values here. So if we go back over to our problem, so that means our solution means our solutions are that x is equal to pi over 3, 2 pi over 3. So those are both radians. Or it's the kind of equivalent degrees, 60 degrees or 120 degrees. Okay, awesome. So now let's look at part B. Part B is asking, when is cosecant of theta equal to -1? So if we remember what cosecant theta is just 1 over sine theta. So this equation is equivalent to 1 over sine theta equals -1. Just using some basic algebra, right? We can multiply both sides by sine theta, right? And actually, even simpler than that is we're just going to use some logic. Okay, 1 divided by sine theta is equal to -1. The only way 1 divided by anything equals -1 is if that thing is -1. So sine theta equals -1. So that's what we're looking for here. So again, we can come back over here, remembering that that sine is a y value. So if we look within one rotation, y value is -1 here. So we're looking at 3 pi over 2 or 270 degrees. So that means our answer is that theta is equal to 3 pi over 2 or 270 degrees. So that's how we solve it within this first rotation. A lot of the times it's going to be the easiest thing to do using our unit circle. Now, let's look at this next problem here, and we've got a little more complicated situation going on, but still pretty simple. Okay, we're going to follow the same steps that we would with any other equation. So right here, it says solve the following equations, assume solutions are in radians. Okay. Now, notice it doesn't say to only give them on 0 to 2 pi. So this wants all of the solutions. Now you may be going like, well, we just did this really simple. We had sine and cosecant. Now we're jumping. We've got this crazy thing. But you guys are master algebra workers, right? You guys can handle this. So I'm going to replace cosine x with y just for an example. Okay. This isn't necessarily something you need to do. But if I give you an equation, y plus the square root of 3 equals negative y, well, how are you going to solve this? Of course, right? Anytime we have something like this, we need to get all our variables to one side, all of our non-variables to the other, right? So we subtract root 3, add y to both sides, right? Subtract root 3, add y. Those cancel, we get 2y equals negative root 3, divide by 2. Maybe that y equals negative root 3 over 2. Well, we're going to do the exact same thing over here, except instead of y, we have cosine x, but it's still the exact process. So I'm going to add cosine x to both sides and subtract root 3. So those cancel. Cosine x plus cosine x is just 2. Cosine x equals negative root 3. Divide by 2. Cosine x equals negative root 3 over 2. Okay, so let's come back over here and look at our unit circle. So we're looking for cosine to be negative root 3 over 2. Cosine is our x values. So we're looking for when is our x value negative root 3 over 2, and that happens both here and here. So we're saying assume all solutions are in radians, so we don't need to worry about degrees. So we're looking at 5 pi over 6 and 7 pi over 6. Okay. So that means that x equals 5 pi over 6. Now, we aren't told that this is on the within one rotation. And so what we have to do is we have to include all coterminal angles. And the way we do that in something like this, the way we would include all coterminal angles is we would say something like this. So we'd say 5 pi over 6 plus 2n pi. And so this is just simply taking n, and we're going to set what n is in just a minute. And our other solution was 7 pi over 6 plus 2 n pi. And you can say 2 pi n if you want, right? Just kind of whatever is comfortable for you. And what we have to specify is what is n. And we say n is an integer. Okay, and symbolically, the way we'd say this in math is n. It looks like this, and this little symbol here that kind of it's kind of like an E. If I draw it really carefully, it kind of looks like this. So it's not like an arrow. It's not me drawing a bad arrow. Okay, it's actually like an E, and that means it's an element of or part of, and then this Z here with this double line is the set of all integers. So what this means here is that n is an element of Z, and that's the way we would read that. And what it means is n is an integer. Okay, and so that's kind of what we would say. You could do either one, either this or this, whichever makes more sense to you, whatever you're comfortable with. But it is important that you specify that, right? If you just gave me the answer that x equals 5 pi over 6 plus 2n pi and 7 pi over 6 plus 2n pi, that is not a complete answer because you haven't told me what is n. Because is n 0.5? In which case, that's not the right answer. Is n 0.1? Right? What can n be? So we want to make sure we specify that. So let's look at the next problem. 3 tangent squared theta minus 1 equals 0. Well, we do the exact same thing we've done, right? We're going to isolate tangent of theta. And so this time we just have a little more. So we're going to add 1 to both sides and divide by 3. So add 1 is 3, tangent squared theta equals 1. We're going to divide by 3. We get tangent squared theta equals 1/3. To get rid of that squared, we just square root. We get tangent theta equals plus or minus root 3 over 3. Actually, instead of that, I'm going to do 1 over root 3. Makes it a little easier. Now we rationalize this, right? We get that. And so notice here, right, in the past when we did square rooting both sides, we said we didn't need to worry about the negative. That was when we were dealing with like finding the hypotenuse and things like that. And so we were doing simply a length, and so it had to be positive. But here, tangent can be both positive or negative. So what we end up with is we end up with essentially two equations. We end up with tangent of theta equals positive root 3 over 3, and tangent of theta equals negative root 3 over 3. Okay, so those are rationalizations of those, right? We rationalized those denominators, so instead of 1 over root 3, we get root 3 over 3. So how do we do this? Well, we need to look over at our unit circle and identify which angles have either positive root 3 over 3 or a negative root 3 over 3 for their tangent. And if you remember, tangent is the y value over the x value. So we come back over here and we look. And so we know we need a positive version. And so we can get that from this first quadrant here. So we're looking for a root 3 over 3. And since it's y over x, let's look at this first one here. We end up with 1/2 over root 3 over 2, which, if you remember, right, that's 1/2 times 2 over root 3. Our 2's cancel. I get 1 over root 3, which is root 3 over 3. So this is what I'm looking for. I'm looking for this point here. Now, what's really kind of fun and really kind of cool is that we can have, we want this both positively and a negative version, right? Because we had that plus or minus because of that square. If it wasn't squared, we'd only want the positive version or only the negative version. So I know to get tangent of theta equal to positive root 3 over 3, I want to have the angle pi over 6. So I know the solution here is that theta equals pi over 6. Now again, we're not told theta equals pi over 6. Again, we're not told that we want these angles just from 0 to 2 pi, so we need to include all of them. Now, if you remember from graphing trig functions, the period of the tangent function is only pi. So whereas cosine, we added 2n pi, here we are only going to add n pi. Because if we think about this to a different color, so we've got this angle here, but if we also go with this angle here, go with the flip of it, that also gives me negative root 3 over 2 and negative 1/2. When I do negative 1/2 divided by negative root 3 over 2, that's going to end up with a positive root 3 over 3. So we only go half a rotation around. And similarly, for tangent of theta equals negative root 3 over 3, we still want the same x and y values in that we still want the x value to be root 3 over 2 and the y value to be 1/2. But now we want to end up with a negative value, and that is this guy here. So that means that this solution for tangent of theta equals negative root 3 over 3, we're getting theta equals 5 pi over 6, again, plus n pi, because tangent has a period of pi, not 2 pi. Okay, so we've done 4 examples. I've thrown a lot at you, right? And so I just want to kind of recap really quick. Whenever we're solving these, what we want to do is we want to first solve for the solutions within 0 to 2 pi. And then from there, we need to assess whether or not the problem has specifically asked for those values, or if it wants all of the values. If it wants all of the values, such as in example 2, we want to make sure we give all of those possible values. Okay, so what now? Well, take a deep breath. Let's do another example. Just like any other problem, we have to worry about the basic algebra concepts, basic algebra structures to solve this. So I have 3 cosine of x plus 3 equals 2 sine squared of x. Now, the thing here is that I've got both cosine and sine, but I don't want to worry about that yet. What I want to worry about right now is very simply, I want to get all of our terms with a variable in them, so in this case the x, on one side. And so I'm going to do that by subtracting 3 cosine x from both sides. And so, zoom in a little bit. So what I end up with here is I end up with 3 equals 2 sine squared x minus 3 cosine x. Now the problem is I don't want to deal with this in terms of trying to find a sine and a cosine and balance this out. So I want you to think. I don't want you to do it. I want you to pause the video if you need to, and to think, how can I get this into so that I have only one trig function, not sines and cosines. I want to have one type of trig function. Okay. So I want you to pause the video and think about how can you do that. Pause the video. All right. Welcome back. So for those of you who figured out, awesome job. For those of you who are totally stumped, that's fine. Let's talk about this. Think back to what we did last section and the section before. We used trig identities to convert trig functions and to manipulate them. Those rules still apply. Those identities still exist. And we have sine squared here, which we can use the Pythagorean identity to change that. And so what it ends up with is we end up with 3 equals 2 times 1 minus cosine squared x minus 3 cosine x. Awesome. So now let's just do some distribution here. 3 equals 2 minus 2 cosine squared x minus 3 cosine x. Subtract 2. 1 equals negative 2 cosine squared x minus 3 cosine x. So now that we have this, what do? Well, if it's hard for you to see it from here, let's replace cosine. Let's let y equal cosine of x. And if we do that, I get the equation 1 equals negative 2y squared minus 3y. And hopefully from here you should be like, this is a quadratic. Perfect, right? And so to solve a quadratic equation like this, we always want to get it in relation to 0. And because I've got negative 2 cosine and minus 3, what I'm going to do is I'm going to add 2 cosine squared x. I'm going to add 3 cosine x to both sides. And those cancel. And what I end up with is 2 cosine squared x plus 3 cosine x plus 1 equals 0. Now, how do I factor this, right? If we were to think back to over here to this with y's, what we now have is we have 2y squared plus 3y plus 1 equals 0. And this actually factors really simply. Excuse me. For those of you who are looking at this going like, oh my God, I don't know how I would ever factor this, right? That may be something you want to go back and practice. You guys are at home. You have some pretty easy ways to kind of help practice through these things. Khan Academy is they have some great factoring videos that you could go back and look at. This factor is simply to be 2 cosine x plus 1 times cosine x plus 1 equals 0. Okay? So, what does this tell us? For those of you who remember how to solve quadratics in factored form, right, and this isn't fully factored form because we have that 2 cosine x, right? We just need to figure out what makes each piece 0. So from this right piece here, that's easy. We get from this, we get that cosine of x has to equal -1. From this left piece here, it's a little more challenging, but we get the same idea. Subtract 1 if you want to set it equal to 0, subtract 1 divided by 2. We end up with cosine x has to equal -1/2. So now we have 2 equations. We can go to our unit circle, we can get our solutions, and it's really, really easy. Cosine x equals -1 only one time, and that's only at pi. So that one's easy. Cosine, not cosine. X equals pi plus 2 pi n. Now cosine of x equals -1/2. So cosine is our x value. X value is negative in the third and fourth quadrants. And so this is going to be x equals 2 pi over 3, again, plus our 2 pi n, or 2n pi. And it's also going to equal 4 pi over 3 plus 2 pi n. And for all of these, n is an element of z. And so this is our, what we'll say is our system of solutions, or our infinite family of solutions to this equation up here, this part C. So it was a lot of work, but if you look at this, we really didn't use any trigness with the exception of the Pythagorean identity in that kind of third step there where we change sine squared into 1 minus cosine squared. But other than that, it's a lot of algebra. And so that is why this is really kind of a nice application of the things you've been doing pretty much every math class up until now, moving those algebra pieces around, manipulating the equations, and so forth. Now, this right here is the exact reason why it's not a great idea to always just convert our equation into something like this. And the reason why is because then you don't see things like sine squared needing to convert to 1 minus cosine squared. You lose that aspect. So make sure you guys are kind of careful with how you guys are manipulating these and working with these, and you aren't making silly mistakes like that. So, page 1 down, right? You might be a little terrified now. Take a break if you need to. Pause the video, come back to it. Let's work on example 4. The rest of the video won't be quite as intense. We are going to use some calculators in some spots to kind of help us out with some of these things. But it's going to be a little bit simpler. So let's solve the equation. Tangent squared theta minus 3 equals 0. On the interval, 0 is less than or equal to theta is less than 2 pi. So it's really nice. We're just wanting to solve this on one positive rotation, so we don't need to do this 2 pi n or pi n since it's tangent or anything like that. What's nice is this is really easy, right? I have tangent squared theta minus 3 equals 0. So add 3 to both sides, giving us tangent squared theta equals 3. Square root both sides, and we get tangent theta equals plus or minus the square root of 3. Okay, so tangent of theta equals root 3, and tangent of theta equals negative root 3. We go back to our unit circle up here. Okay, when we had 1/2 over root 3 over 2, all right, which is what we got with pi over 6, that ended up with 1 over root 3 or root 3 over 3. So that means if I flip that, so I look at this piece here, root 3 over 2 over 1/2, root 3 over 2 times 2 over 1 And that's just root 3 over 1 or root 3. So we're looking for points on here that either have 1/2 and root 3 over 2 as 1/2 as the x and root 3 over 2 as the y, give or take signs, right? So for tangent of theta to equal root 3, so positive root 3, that happens both at pi over 6, or sorry, pi over 3. So pi over 3 here. But then also at 4 pi over 3, because negative divided by a negative is positive. So that means this gives us the solution of pi over 3 and 4 pi over 3. Similarly, when tangent theta equals negative root 3, you can look at the unit circle and you see that you'd get 2 pi over 3 and 5 pi over 3. Okay, so that one was pretty easy, right? But notice that because it wanted us within one full rotation and we're dealing with tangent, which has a period of pi, we actually got 4 solutions. If this was sine squared of theta minus 3 equals 0, we would only get 2 solutions within that rotation. Same with cosine. But because tangent has a period of pi, we got 2 solutions for theta, or for positive root 3, and we got 2 solutions for negative root 3. So let's move on. Find all solutions for 2 cosine t minus 2 sine t equals negative 2. Okay. Well, the hard thing here is to kind of figure out, how do I deal with this when I've got cosines and sines, and this time I don't have any of them squared, and so it doesn't really help me out. And the way we do it is kind of tricky in a way. And the first thing we do is let's get rid of these 2's, right? If we just divide everything by 2, divide by 2, right? Those all go away. So what I end up with is cosine t minus sine t equals negative 1. Now here's the trick. I'm going to square both sides. Okay. Now the right-hand side just becomes positive 1. The left-hand side I have to distribute and use FOIL, and what we end up with is cosine squared t minus 2 sine t cosine t plus sine squared t equals 1. Now what's cool, use the highlighter, I have cosine squared t plus sine squared t. What does that equal? That equals 1. So gives me minus 2 sine t cosine t plus 1 equals 1. Subtract our 1. Negative 2 sine t cosine t equals 0. So what I have here is I have the product of 3 things. I have negative 2 times sine t times cosine t. And all of that is equal to 0. And the only way that ever is equal to 0 is if one of those 3 pieces equals 0. Right? So this is a times b times c equals 0. The only way that's true is if either a, b, or c is 0. Negative 2 is never going to be 0 because it's negative 2. So that means our solution to this equation happens either when sine of t equals 0 or when cosine of t equals 0. Now, what do we do? We need to look at this and we need to see when these are true. And that's really easy. Sine of t equals 0 when t equals 0, and pi. Cosine of t equals 0 when t is equal to pi over 2, and 3 pi over 2. Now, unfortunately, we are not done. And the reason we're not done is because of that second move we did, that squaring both sides. Because what we could end up with now is things like 2 equals negative 2. Because if I look at 2 equals negative 2, is that true? Right? Absolutely not. But what if I square both sides? If I square both sides, 2 squared is 4, and negative 2 squared is 4. Now that's a true statement. So the easiest way to check these is very simply just to plug in 0, pi, pi over 2, 3 pi over 2 back into your original equation. And I would do this using a calculator. Okay. Unfortunately, I don't have a calculator to show you guys on here. So what you're going to do is very simply make sure your calculator is in the correct mode, right? Make sure your calculator is in radians mode. Go to your y equals, okay? And you're going to input in this original equation. So 2 cosine of t minus 2 sine of t. And for the t, you're just always going to use that variable button, which should be to the right of alpha if you're using an 83 or a TI-83 or a TI-84. If you're using a different calculator, just make sure whatever variable button you need to use is the one you're using here. Once you have that entered into your y equals menu, these steps are in 83 or 84 only. If you have a different calculator and you want to know how to do it on your specific calculator, email me. We can set up a time to meet, or I could just message you kind of the quick, dirty version if it's a simple thing. So once you have that, you need to set up your table in a great way. And the way you're going to set up your table, so to do that, again, this is 83s and 84s. You're going to press second and then window. So window is right next to y equals. And it should say TBL SET above it. And when you do that, it should give you a little screen that says table setup. And then there should be about 4 rows. You may see a table start, a TBL start, a little triangle TBL. So that's kind of what the jumps are. So if you say start at 0 and then the triangle table is 1, it means your table is going to go 0, 1, 2, 3, 4. If you set that triangle to say 0.5, it's going to go 0, 0.5, 1, 1.5, 2, 2.5, and so forth. I don't care about the first 2 rows. What I want to do is I want to go down to the 3rd row, which should say INDPNT. It stands for independent. And I want to go highlight ask and hit enter. And then under the next one, the dependent, I want to highlight auto and hit enter. In doing that, it allows us to go into our table and input whatever input we want using our table, and then to automatically see the output generated for us. So if you do that, okay, you've got your table set up, go over to table. So you should have your functions typed into your y equals. Go to our table, and what we're just going to do is very simply, you're going to hit, so with the X row list highlighted, you're going to hit 0, hit enter. You're going to hit pi, hit enter, pi over 2, hit enter, and 3 pi over 2, and hit enter. And each time you do that, you should see a y value populate to the right of that. If you did it in this order, your y values should look like 2, negative 2, negative 2, 2. Okay? And so what that means is that if x is 0, or in this case t is 0, we end up with the equation 2 equals negative 2, which is not true. So t equals 0 is not a solution. And the last one, 3 pi over 2, again, we get the same thing. So that is also not a solution. So that means our final answer to this example 5 is that t is equal to pi over 2 or pi. Okay. I know it's a lot. Hopefully that makes sense. This trick of squaring both sides is not a very common trick that we're going to do. It is something that you may need to use. And so if you're getting through and solving something, you're like, man, I'm stuck. I don't know what to do here. I've got sines and cosines, but nothing squared. Try squaring it. See if that helps, right? Remember, this chapter is the chapter where it is very okay to get through, get stuck, realize that's not the right path, and go back and try something new. This is a very kind of exploratory chapter in that method, in that way. Okay. Now, let's do example 6. Example 6 is really easy. And the reason why it's really easy is because we aren't doing anything too crazy. What we're doing is we're just solving sine of 15t equals root 3 over 2. The first step in doing that is to essentially ignore the 15t and just solve sine of theta, if you will, equals root 3 over 2. And so in doing that, in solving that, which I believe, was that our first problem? Yeah. We get pi over 3 and 2 pi over 3. Okay. The difference here is we aren't looking for that first rotation. So what we get is, so up there in the first problem, you go back and look at it, we have that x equals pi over 3 and x equals 2 pi over 3. Here, instead of x, it's 15t. So we get 15t equals 2 pi, oops, meaning equals pi over 3 plus 2 pi n. And we also get 15t equals 2 pi over 3 plus 2 pi n. Now, instead of dividing, dividing is perfectly correct and absolutely works. And if you can figure that out and go through that with your mental math, it's great. But what's maybe a little easier to visualize is multiplying by 1/15. I'm going to do that on both sides of both equations. Okay, so obviously these cancel and I just get t equals, right, same thing here. Now I have pi over 3 plus 2 pi n times 1/15. So I need to distribute that 1/15. So I want to distribute that 1/15. When I do that, I get pi over 45, because pi over 3 times 1/15, that, plus 2 pi n over 15. And over on this next one, we get 2 pi over 45 plus 2 pi n over 15. And we need to also make our statement that n is an integer. All right. So the only real difference here was we solved the original trig function, the trig equation, and then we had to do this one extra step in this case, which was just dividing by 15 or multiplying by 1/15 to get rid of that extra piece. And if it was, say, 15t minus 6, right, we would add 6 to both sides, and then we would multiply by 1/15. So really the same process either way. Very straightforward. Example 7 is a little more challenging for us on here, only for the reason that I don't have a calculator to show you guys this. But it's really easy to do, and as it says, to do it graphically. So you're going to use your calculator for this. Okay. The first thing to do is get all of your variables on one side. So we're going to subtract theta from both sides. It cancels. And I get 0 equals 0.26 plus 0.017 sine of theta minus theta. And so this is what we're going to do differently than we did in that part before where we put it y equivalent to the table. Because there we had 4 values and we just wanted to test them and check to see that they worked. Here, we are looking to solve this. And the way to do that is you're going to use your calculator and you are going to put this into the y equals menu. And then you're going to graph. And once you've graphed it, then, okay, I'll write out these steps on this one. You're going to hit second, and then get to the calc menu. Okay, if you look, that is the button that says trace on the main part of it, which is right next to the graph. Okay, from there, you're going to choose option 2, 0. Okay. Okay. This should give you some graph. And if you look at your graph, if you're just in standard, it looks like it goes through the origin. But it doesn't quite go through the origin. It's just a little off. And if you zoom in once, you'll see that it's definitely not the origin. So once you do calculate and choose the 0, it's going to take you back to the graph, and you're going to see a thing that says left bound. Okay, that's just asking you if you move the cursor, if you press the left and right arrows, you'll see there's a little thing that moves around on your graph. You just want to get that to the left of wherever you think that 0 is. Okay, you hit enter once you do that. Then you're going to use the right arrow and to move that little thing to the right of wherever that 0 looks like it is. And then guess, you could move it close to where you think the 0 is, or you could just hit enter. It doesn't really matter. And in this problem, what we end up with is theta is approximately, that's all terrible. Theta is approximately 0.264. And that's it. That's all you have to do. Okay. If you are unfamiliar with using your graphing calculator to solve equations graphically or to find the zeros, I definitely recommend Googling. Just go to Google, whatever type of calculator you have. So if you have an 83, if you have an 84, if you have a TI-89 or something like that, or you have a Casio, just Google solving equations graphically using a TI-84 or a blank insert calculator name here. Okay. All right. Now, let's keep going. I have the inverse tangent of 3x plus 7 equals pi over 4. Well, how do I get rid of inverse functions? You just put the regular function in, right? So I'm just going to take the tangent of both sides. So that gives me tangent, inverse tangent of 3x plus 7 equals tangent of pi over 4. Tangent of inverse tangent cancels, giving us 3x plus 7. And the tangent of pi over 4 is 1. This is an easy equation, right? Subtract 7. We get 3x equals negative 6 divided by 3. X equals negative 2. Awesome. Next one. Well, that looks a lot crazier, right? But it's not, right? Notice we have inverse cosine of x and inverse cosine of x. We just have 2 times it and 6. So this is no different than if I just said 2y plus 6y equals 2 pi. Combine like terms. So these are like terms. So I end up with 8 inverse cosine of x equals 2 pi. I don't want to take the cosine of both sides yet. I just want to simply divide by 8, giving me inverse cosine of x equals pi over 4. Now I want to take the cosine of both sides of this. Cosine inverse cosine cancel. We get x equals simply cosine of pi over 4, which is the square root of 2 over 2. So if you have an equation involving the inverse trig functions, and especially if it's only that, I'm not going to give you anything like with inverse cosine of x plus sine of x. I'm not me. So if you have inverse, just take the trig function of both sides and get rid of those inverse functions. Okay. So let's move on to our next thing here. Our next thing here is this definition. And so what we are defining is something called a reference angle. So A reference angle for a given angle theta. We write this theta sub r. Okay, that's how we'll typically write it in this class. Occasionally, you may see it as theta with this apostrophe, which we'll read as theta prime. So we would say this as theta prime. I don't like that. Theta prime, and this here is theta sub r. Okay. What this is we are looking for an acute angle, okay, in standard position that is made by the terminal side. Sorry, not in standard position, but an acute angle made by the terminal side that is using the x-axis, not the y-axis, but the x-axis. So what's nice is if we have an angle in the first quadrant, okay, so here's theta. Theta r is the same. But if we have it in the second quadrant, so this is our angle theta, theta r is this angle here. Okay. Third quadrant, so this is our theta. Theta r is just this angle here. And lastly, in the fourth quadrant, that's our theta. And this is our theta r. Okay, so visually speaking, this is our reference angle. And so what this is used for is it's used to help us in solving these equations. And so the first thing we want to practice is just finding these reference angles, okay? So I have 4 angles here. I want you guys to practice this. If you guys haven't, if you think, all right, I got this, I want you guys to pause the video, identify the reference angles for these 4 angles, and then play the video again. If you want to watch an example or two, pause the video, then do the rest by yourself. Okay? Try to kind of work some of these as best you can on your own. Draw these out. Don't just try and mentally think and be like, it must be this, right? It's so much easier if you draw them out. So we are looking for theta equals 120. We want to find that reference angle. So 120 degrees is going to put us over here. So this is 120 degrees, which means our reference angle is right here. So what we're looking for is how much farther do we have to go to get to 180 or straight angle, and that is 60 degrees. So that means that theta sub r equals 60 degrees. We have 85. That's in our first quadrant. This right here is 85 degrees, which means that theta sub r is 85 degrees. That's easy. Okay. 7 pi over 6. Which quadrant is 7 pi over 6? Right. So 6 pi over 6, or pi is 180 degrees, right? So that gives us half rotation. So we are 7 pi over 6. So we're just a little bit more than that. So we are over here. This is 7 pi over 6. So that means our reference angle is right here. And so how far do I have to go from 7 pi over 6? And so if you kind of look, we're kind of going backwards, right? Because we're trying to figure out to go back up to kind of like pi. Well, I have to go back just pi over 6. Okay, if you think about it, we're at 7, 6, and I want to get to 6, 6. I have to go back 1, 6. So that means that here, theta r is pi over 6. And our last one, we have negative 3 pi over 4. That is in the third quadrant as well. Negative 3 pi over 4. Our reference angle is just this, And that's, so how much farther do we have to go to get to pi? And that's just a pi over 4. So theta r equals pi over 4. So we can even find reference angles for negative angles. It doesn't matter whether it's a negative angle, a positive angle, whether it's within 0 to 2 pi, or whether it's, we could look at the angle, say 16 pi over 3. We can find a reference angle for that angle. And so ultimately what it just comes down to is finding where that terminal side is and figuring out how far we have to go to get back to the x-axis. Okay. Now, here's a cool little useful tidbit. If theta is an angle in standard position with a reference angle, theta sub r, okay, then what we know is that the absolute value of the sine of theta is equal to the sine of theta sub r. Absolute value of cosine of theta is equal to cosine of theta sub r. Absolute value of tangent of theta is equal to tangent of theta sub r. And exactly similar with all of our other trig functions. Cosecant of theta is equal to cosecant of theta sub r. Absolute value of secant of theta equals secant of theta sub r. Absolute value of cotangent of theta equals cotangent of theta sub r. Okay, so what we have here is that the trig value of the original angle in standard position is equal to the trig value of the reference angle, give or take a plus or minus. And what's cool is these signs of the trig values, these trig functions, are determined by what quadrant they fall in. And this is something that if you are kind of blown away by this fact, go back to our unit circle. Okay, and remember that, say, sine is y. So that means in quadrants 1 and 2, sine is greater than 0. But in quadrants 3 and 4, sine is less than 0. Okay, so we can do that with all 6 trig functions, and we can kind of figure those out. Let me just jump out and jump back in. Okay, so now we're going to use this to solve so we're looking at, on, again, one positive rotation, when sine of theta is equal to negative 1/2 in degrees. And the way we're going to do this is we're going to use reference angles. Okay, so what I know is I know that sine of theta sub r is equal to the absolute value of the sine of theta, which is just the absolute value of negative 1/2, which is 1/2. So I know that the sine of theta sub r of the reference angle is 1/2. Okay. So remember, our reference angle is an acute angle, so it's between 0 and 90 degrees. Okay. Which means that theta sub r is equal to what? Well, it is equal to pi over 6, or anybody? 30 degrees. Okay. So theta sub r is equal to 30 degrees. Now, how do I know which angle, whether it's a positive one or a negative one? Well, what I know is that my sine was negative. And as I just wrote up on the unit circle, that only happens in the third and fourth quadrants. So that means I know this angle is either here or here. So what I'm looking for is I'm looking for this angle and this angle. Because it's solve the following on 0 to 360. So we aren't looking at the negative angles or any of that stuff. And I know that for both of these, this measure is 30 degrees. So if this measure here is 30 degrees, well, this measure is 180, go 30 more, and we get to 210 degrees. And if over here, an easier way is the whole thing is 360, go back 30, and we get 330 degrees. Okay. There you have it. So this is how we're able to find these values. Because if you just take inverse sine of -1/2, remember, inverse sine only gave us values here, right? It had an output of -π/2 to π/2. That doesn't help us in this problem, right? It would have told us it's -π/6. That is inverse. If we take inverse sine of both sides, the theta is -π/6. That's not the whole story. And so we need to be able to use these reference angles to kind of help us out. There's no better help than drawing these graphs, okay? Drawing these images here makes this 1,000 times easier. If you do not draw them, you try to think, well, if theta sub r is 30 degrees, then it's just a monster. And if you have the brain power and your brain works that way, that is awesome. More power to you. But it doesn't work that way for me. So now I want to use some basic algebra to do this. So we're going to subtract 2.3 from both sides, giving us 1.7 times the cosecant of t, -2.3, divide by 1.7, cosecant of t is equal to, and let's see here with our calculator, 2.3 divided by 1.7, 1.3529411176. Okay. But you know what the problem with that is? So actually, yeah, I'm going to leave it -23/17. So that decimal is really gross. It's not a nice, if it was like something like 0.25, I'd leave it, but it's not. So I'm going to convert this into a fraction. If we just use math fraction in our calculators, -23/17. The reason why I want to leave it like that is because I don't want to deal with cosecant. Ew, no, I want to deal with sine. And so to convert this, that means if cosecant of t is -23/17, that means that sine of t is -17/23. Which that, if you want to, is approximately 17 divided by 23 is 0.74739, -0.739. Okay. So, how do I work with this? Okay, to find our reference angle, T sub r. So, sorry, quick note. We're in radians. So to find T sub r, that's equal to inverse sine -0.739. I'm jumping myself all over the place. So sine of t equals negative 17 over 23. That means that sine of t sub r is positive 17 over 23. That's what I want to use. And the reason why is because that's going to give me an acute angle. It's not going to give me a negative angle. It just makes it life easier. And you're going to see why in just a sec. So that means that t sub r is inverse sine of 17 over 23. You can do that on your calculator. Just use the inverse button. And to do that, to get the inverse trig function, you're just going to hit second and then the normal trig function button. Again, that's 83s, 84s. Make sure you're in the right mode. And so what we get here is we get that t sub r is approximately 0.832. Okay. Again, sine is our y values. Y values are negative in the third and fourth quadrant. So what I have is an angle here, an angle here, such that this is 0.832, this 0.832. Now, with degrees, it was really easy, and we had nice numbers. But here we don't quite have the nice, pretty numbers, but it's still fairly simple. I know that this distance, that angle is pi. So to figure out what this angle is here, to figure out what that t is, it's just pi plus 0.832. And we get 3.973. Over here, t is equal to 2 pi minus 0.832. And we get that t is approximately 5.451. And so that gives us our trig values here. Okay. All right. So what we did here is first we isolated our trig function, and then we converted it from, in this case, the cosecant into the sine. And the reason we did that is because we have the ability to take inverse sine and inverse cosine. We don't have the ability to do inverse cosecant on our calculators. So once I got us to sine of t equals negative 17 over 3, I don't want to deal with a negative. And so what I'm going to do is I'm going to use my reference angle and then inverse sine of both sides. Use that along with drawing some images to figure it out. Last example, we're almost done. We are in the home stretch right here. We're going to start this off in the exact same manner. I'm going to subtract 2, divide by 6, and I'm going to jump that because I feel like you guys are so smart. You guys know that that's going to end up with negative 1/3. So cosine of t equals negative 1/3. Again, I don't want to deal with negative, so that means I want to look at cosine of the reference angle here, and that's just going to be positive 1/3. So that means that t sub r is equal to inverse cosine of 1/3. T sub r. Again, we are in radians, so t sub r is approximately 1.231. Now, when is cosine negative? Cosine is our x. So that means that happens in the second and third quadrant. So that means we're here. That means that's t. Or we're here, with that being t. Our reference angle, our 1.231, is here and here. So what we're going to do from here is we're going to do a very similar thing to what we did on part B, right? On part A, because we had degrees, it was a lot easier. We saw 210 was, or we saw 30. We knew that was 180, 180 plus 30. So we didn't write it out, but we did the same idea that we did here. So what we just kind of need to figure out is what's the nearest angle that we know. In other words, kind of what's the nearest x angle. So are we at If it's an acute angle, we would be looking at 0, which is just easy. If we're in the second quadrant, we would be looking at 180 or pi. If we're in the third quadrant, we're again looking at pi. If we're in the fourth, looking at 2 pi. So to figure out t in this first one, we're going to take pi minus 1.231. The reason why we're subtracting is because pi is a full 180 degrees or all the way back to the x-axis, and we want to go less than that. And when we do that, we get that t is approximately 1.911. And here we're going to do that t is equal to pi plus 1.231. So that gives us that t is approximately 4.373. Like that. T approximately 4.373. All right. There we go. Whew. So there's a lot of different ways to solve trig equations. If we go back to the very beginning, okay, if we look at these up here, okay, we were solving trig-valued functions or trig functions when they were equal to things that we knew were on the unit circle. So we're looking at things like tangent of root 3, cosine of -1, sine of root 3 over 2, right? Things like that, things that we knew are on the unit circle, and so we're able to solve those really easily, okay? And then we did a problem where we didn't have those values on the unit circle, but we could use a calculator to graph it, and we could get that nice, easy thing. That is not something you want to do when you're dealing with a more cyclical natured function. Example 7, because we had that theta by itself, allowed us to kind of do that. But any other time, you have all of these kind of problems, and like these last ones here, we want to use reference angles. Now, that first problem, you're like, hey, sine of theta equals 1/2. We know that because we have the unit circle that's on there. Yes, and that's why I did that one for the first one, because if you don't trust that I did that right, or you don't think that reference angles work or whatever, you can go back and look at your unit circle and be like, oh, okay, that is, he's not lying. But if we look at B and C, we don't have cosine equal 1/3. We don't have sine equals -17/23 on our unit circle. So we have to use what we can do using these reference angles and our inverse trig functions on our calculator to evaluate these. And so that is how to solve these trig functions. Make notes to yourself, right? And if it's not clear already, it's a good idea to have maybe a second note sheet with this like quick hit notes, right? So like, if this, then this, right? If we're solving a trig equation and it's dealing with a value that's on the unit circle, just use the unit circle. If it's not on the unit circle, use a reference angle, okay? And I can't emphasize enough, draw these graphs out. It is so important and so vital to do that, because if you don't, it just leads to a lot of silly mistakes, a lot of silly like, oh man, I thought that was the first and second quadrant, not the second and third quadrant. I messed that one up. So make sure you draw those out. And with that said, guys, good luck on the assignment, and I'll see you guys in 7.4.